Today we're going to explain you the principle of the conservation of angular momentum. Now, I already see you frowning. I know it sounds difficult, but we're going to show you that it's not as difficult as it sounds. We are going to follow the ice skater Lucy through her day, and she will help us to explain you the concepts needed to understand the conservation of angular momentum. Are you ready?
As Lucy wakes up, she starts her day with a nice breakfast. Her turning cheese plate allows us to introduce the angular motion. Lauriane, could you give us some more information, please?
As you all know, we have three key variables to describe the linear motion, namely the displacement, the velocity, and the acceleration. Now, in rotational motion, we find three equivalent variables to describe the angular motion, namely the angular displacement, the angular velocity, and the angular acceleration. So suppose we have Lucy's cheese plate here. Now we have here the initial angular coordinate, and if I turn the cheese plate until there, the first thing that we will want to describe is how much angle the object has rotated through. Now, to describe this, we have the angular displacement. The angular displacement with the sign delta theta. And what's the angular displacement? Is the final angular coordinates minus the initial angular coordinate. Why? Because it's the displacement. So we want to know how much angle the object has rotated through. So what about angular velocity? Well, it's similar to linear velocity, but now in rotational motion. So we have here the angular velocity equals the change in angular displacement over time, and it's in radians per second. Now the angular velocity is a vector, so of course it has a direction. Now the convention says that if an object is rotating clockwise, the angular velocity is negative. And if an object is rotating counterclockwise, the angular velocity is positive. And lastly, the angular acceleration. Now, the angular acceleration is the change in angular velocity over time. It's in radians per second squared, and the angular acceleration is also a vector. Now, what about the direction? So if the object is speeding up, the angular acceleration and the angular velocity are in the same direction. If the object is slowing down, the angular acceleration and the angular velocity are in opposite directions. I hope it's clear for you now.
Thank you, Lauriane. After her breakfast, Lucy leaves her home. When noticing she forgot her scarf, she tries to reopen the door by pushing it at the hinge. She struggles. She then tries to push the door at its edge, and it suddenly easily opens. So, how come she struggled at first?
I have a simple explanation for this. Let's look at the door that Lucy pushed from above. If Lucy pushes the door is going to rotate around an axis called the rotational axis. Here, our rotational axis is I3. So let's take Lucy. She's pushing the door around the rotational axis and with G a point on the rotational axis. And we saw that in the beginning, she pushes the door near the hinges of the door. And the force is not effective since the door doesn't open. Here, Lucy pushes the door far from the hinges, here. Now, we have two forces, here and here, with the same magnitude, the same direction, and the same orientation. So the difference between the effectiveness of both forces must be due to the point of application of the force. Here we see that the point of application is near the axis of rotation, while here the point of application is far away from the axis of rotation. The difference is more precisely in the distance between the point of axis and the point of application of the force, and here the point of axis and the point of application of. Now, in linear motion, we saw that a force causes an object to move. In rotational motion, a torque causes an object to move. Now, what is a torque? If we take the torque around a point G caused by a force F equals the lever arm, which I'm going to define, times the force applied on a point on the body. So the torque is a vector, and the lever arm is the distance between the point of axis and the point of application of the force. So here we have the R, which is like really small, and here we have a lever arm that is really large. The lever arm and the force are always perpendicular, since the torque is a vector product of the lever arm and the force. So knowing this, what would happen if we applied a force of the same magnitude, the same direction and the same orientation, but at a different point of application? Let's say here. Now, we see that the lever arm would be like this. Here is the force. And since the lever arm times the force is smaller than in this situation, this torque would be less effective than this one. So what would happen if we applied the same force, but here? Now, let's take the lever arm. We see that the torque would be 0. Why? Because we just saw that the torque equals the cross product of the lever arm and the force. This means that both need to be perpendicular to each other. Since here they are not perpendicular to each other, the torque is 0.
When continuing her day, Lucy is peacefully riding her bike when suddenly she almost got hit by a car. They both did brake just on time. This was a close call.
We can see that it is much more easier to stop a bike from moving than a car. And I'm going to explain to you why. So, imagine a bike and a car riding at the same speed. We can see, of course, that the bike has a much smaller mass than the car. What we call the quantity of movement, or the momentum, is namely the speed times the mass. We can see here that the momentum of the bike is the speed times the mass of the bike, which is of course smaller than the momentum of the car, since they have the same speed, but the mass of the car is bigger. So, because the car has a bigger quantity of movement than the bike, it takes more time for a car to brake than for a bike.
She continues her journey on her bike. As it is a very good example to explain the angular motion, we'll analyze the movement of a wheel.
Let's now focus on some theory. Newton's second law tells us that a force is equal to the mass times the acceleration of an object. Now, if we want to find the rotational analog of Newton's second law, well, we need to find the torque. The torque, as we have seen before, is equal to the force times the lever arm. Here, we won't take the regular force here in blue, because it's not perpendicular to the lever arm. This is why we use the tangential force. Now, because we have multiplied the left side of the equation by r, we need to do the same for the right side of the equation. So, in the left side we have the torque, and in the right side we have the mass times the radius squared times the angular acceleration.
Before going to her ice skating competition, Lucy stops by a distributor to get some water. While looking for money, she lets a ring and a coal fall out of her pocket.
As you can see on the video, the coin is rolling and falling much more further and faster than the ring. I'm going to explain to you why. We can see from our last equation that the torque is equal to the mass times the radius squared times the angular acceleration. Now, this was for one particle. If we want to take it for a body as a whole, we will take the sum of all the torque exerted, which will be then equal to the sum of the mass times the radius squared for each particle times the angular acceleration. So this sum is in fact what we call inertia. What is inertia? Inertia is the distribution of the mass of a body. So, for example, we will sum each particle, mass, and radius squared. So, the ring would have a much bigger inertia than the coin, since most of its particles are situated at a much larger distance than for the coin. This is why, in fact, the coin will be moving faster, rolling further than the ring.
Lucy finally arrives at the ice skating rink to warm up for a competition. When she tries her pirouette, she can't seem to find a good balance. Maybe this balance could be found through an understanding of the angular momentum, but what is it exactly?
The angular momentum is the rotational analog of the linear momentum we saw a few moments ago with Lucy. Now, how do we calculate the angular momentum? The angular momentum equals the lever arms times the momentum, the linear momentum. So the angular momentum is a vector as we see it here, and since it's a cross product of the lever arm and the linear momentum, both need to be perpendicular to each other. So here we have the lever arm and we have the linear momentum. However, we see that this is not perpendicular to this. So we're only going to use the component that is perpendicular to the lever arm. And this component equals the mass times the velocity times the sinus of this angle. If we go back to the angular momentum, we have, to calculate the magnitude, we have the mass times the velocity, but only the component that is perpendicular to the lever arm times the lever arm. So we know that we can relate the velocity and the angular velocity with this equation. If we integrate this equation into this formula, we have the mass times the lever arm squared times the angular velocity. As we have seen before, this equals the inertia. So the angular momentum equals the inertia times the angular velocity of the body. We have seen the angular momentum, but what if the angular momentum changes? Now we will see that the change of angular momentum over time equals the net torque on a body. Now if we derive the angular momentum, we will have this equation. Now we know that if we derive r, we will have the velocity. And if we derive here the velocity over time, we will have the acceleration. Now since it's a cross product and the velocity is parallel to the velocity, this will equal 0. Here we have r times the mass times the acceleration. Now we have seen that, and this equals the force. Now here we have r times f, which equals the net torque.
One of the reasons you don't fall off a bike is because there is an angular momentum associated with the rotation of the wheels as soon as you start pedaling. This can be demonstrated by putting a string at the axis of a wheel and dangling it down. It will thus remain in the horizontal plane unless you spin the wheel. The present angular momentum will then want to keep its direction that is perpendicular to the rotation of the wheel. Thank you, Lorian, for those insights. Lucy seems to have got it. But what is she actually doing with her arms while spinning?
Now we're going to look at the angular momentum conservation. The angular momentum conservation states that if there's no net external torque acting on a system, the angular momentum remains conserved, which means constant. If we look at the equation we derived, we see that the net external torque equals the change in angular momentum over time. If this equals 0, we see that the change in angular momentum over time is also going to equal 0, and thus the angular momentum is constant. Now, what does that imply? If we look at the magnitude of the angular momentum, we know that it equals the moment of inertia times the angular velocity. So the moment of inertia times the angular velocity are also going to be constant. What about a system? If we have a system and there's a change in moment of inertia or angular velocity, so here, for example, this change will have to be compensated in order for the angular momentum, the total angular momentum of the system, to remain constant. Now, if we take Lucy. Lucy is a system, and she's spinning at an constant angular velocity, and there's no net external torque acting on the body. Therefore, her angular momentum is conserved. Now, Lucy has her arms outstretched, and she has an initial moment of inertia and an initial angular velocity. When Lucy pulls her arms in, her mass distribution is going to change, it's going to be smaller, and therefore, her moment of inertia is going to decrease. Now, since the total angular moment of the system has to remain constant, the angular velocity is going to increase in order to compensate the change in moment of inertia. And therefore, the total angular momentum remains constant.
Here our guy is spreading his arms away from his body while holding a bottle of water in each hand. We consider there is some friction between the platform and the ground, and we give him an initial angular velocity. Once he brings his arms back in, we see that he starts turning faster. This is actually due to the angular momentum conservation. Once the moment of inertia decreases, the angular velocity increases. Same thing happens in the opposite way. When he spreads his arms back out, his angular velocity decreases to reach a lower value than the initial velocity due to the friction. You can try this at home. Just sit on a turning chair with two masses in your hands and ask someone to give the chair an initial angular velocity. While turning, you just have to bring your arms in and out. We can also experiment this with a system of two bodies on which the angular momentum conservation applies. In this case, we have the rotating wheel and the person on the chair. If now a directional change of the angular momentum of one body in the system occurs, in this case a wheel deviating in a plane perpendicular to its rotation, an opposite directional change in angular momentum of the second body will counter this. That's why the chair will start turning in the opposite direction. And it's a win for Lucy. She gets to go home with a cup and a gift card for a helicopter ride. Actually, the helicopter is another good example of the angular momentum conservation. Let me explain how. We consider that there is no friction between the helicopter and the air. Once the first rotor, the one located on top of the helicopter, starts turning, we can see that the cabin starts turning in the opposite direction. This is due to the conservation of the angular momentum. This is the reason why there is a second rotor, the red one. This rotor will create a force that will counter the rotating movement of the cabin, which will stabilize the helicopter.
We're at the end, and I hope that everything was clear and that we helped you to understand the conservation of angular momentum. Now, as you saw, the conservation of angular momentum is everywhere and is understandable for everyone.